so much to Professor Navidesan for arranging such a wonderful event for the young geologists. So this talk is about my PhD work, and some of you might have listened to it like 10 days ago in a Savalik seminar as well. So might be it is for some of you it is a repetition, but I think the audience here is very different what we have there. So there are a lot of students. So my request to the students will be to take this talk more like something that how a PhD work actually. So just look at how the research questions are framed here and what methods we have used, and then try to come up with something in your PhD work or in your master's work, how you can take some things out of this and apply it in your work and take us forward through your work in the field of geology. So I would start with my presentation, data structure evolution of Kohat, Potwar, fold and thrust well. Everybody who is a graduate in geology know about Kohat and Potwar in Pakistan. So in a broader perspective, we talk about fold and thrust wells, and they are important places because these places give us an opportunity to learn about the mountain building processes and also about their economic aspects. And one very important thing which just in the earlier talk we have seen that earthquakes that are really, really important. These earthquakes can bring huge devastation for the society. So understanding them is really, really crucial in terms of understanding the economics as well as the sustainability of the society. So starting with the research questions. So fold and thrust wells like in Andes and Alps in Pakistan in terms of Himalaya, the fold and thrust wells show difference in their structure style along and across their strike. For example, here you can see the Himalaya here in this form. The sub-Himalaya between main boundary thrust and main frontal thrust is just 20 kilometers wide. And when you go toward west in the Kangra reentrant, you see it's about 100 kilometers wide, and then it is really, really wide in Pakistan, about 150 kilometers. And also when you look at the timing when these faults are formed, what we see is that MBT is formed around 5 million years in central Himalaya and about 10 million years in the northwestern and western Himalaya. And there are new data that suggest that these main boundary thrusts have been reactivated after its first generation at 10 million years. Same is the case with the main frontal thrust. It is developed about 2 million years in the central Himalaya, which is nearly accommodating all the conversions between India and Asia today. And when you come towards the western side, there are older ages that are associated with the formation of main frontal thrust. In Pakistan, we call it salt range thrust. In northwestern India, we call it Himalayan frontal thrust. So more or less in this talk, you will see main frontal thrust that represents salt range thrust here in Pakistan. So in my PhD, what I did is I looked at the structure style difference between Kohat and Potwar, and I looked at the structure chronology of this area. So what I did is that I did the structural modeling, where I developed the balanced cross section, restored them to estimate the amount of shock being accommodated by different structures, and look at the structure style transition from one side into the other. So this is one of the pictures from my PhD work. And the other thing that I used is low temperature thermochronology. So this was an important tool that actually is done on apatites and helium most commonly. So in apatite helium dating, what we do is that we take out the apatite minerals from the rocks, separate them, and then we put them through a machine known as alphachron. What happens is that the natural decay of uranium, thorium, and samarium, they produce radiogenic helium. And this helium is trapped inside the apatite crystal. So if you quantify the parent and daughter, you get the age of the apatite helium dating in that sense. And the other one is apatite fission tracks. what happens naturally is that uranium-238 produces natural damages in the crystal lattice of apatite crystals, for example, here. So here you see that you can see small cracks inside these crystals. These are known as natural or spontaneous cracks that are produced by natural fission. And what we do is that we put a microsheet on top of these polished sections containing apatites, and we send them into a nuclear reactor for thermal irradiation. And what comes out back is that uranium-235 from the apatite crystal produced some new tracks that are induced into the external detector, in this case that is mica. So in this case, this is the daughter product, and this is the parent product, which actually quantify the uranium ratio in the crystal. So when you quantify the parent and daughter, you get the age of the rocks. And down the line, you will see that these methods are really important in understanding fold and thrust kinematics. So in the first thing, what I did is I looked into the structure style transition from Kohat to Potwar, and like I said before, that there are a lot of studies done in Potwar separately and in the Kohat. So I did this to look into the structure style transition. Hardly you find any study on that. So this was one of the tasks I did. So what you see, second task was understanding the development of the salt range, and the third one was looking at the structural propagation from main boundary thrust to the surrogate thrust in the Kohat, and overall combining them to understand the structural evolution of Kohat and Potwar. So here, the boundary zone between Kohat and Potwar, what you see is the geological map and some of the important thrusts that are present in this area. This is the southeastern part of Kohat. You can see a lot of thrusts and tightly anticlinal folds that are exposed at the surface. But when you go toward east in the Potwar, you see quite subtle stratigraphy there. You don't see a lot of thrusts, and there are kind of gentle to open folds present in the southern part of Potwar. And down in the south, you see that all the strata from Precambrian salt range formation to Eocene for limestones are exposed in the salt range. And there's another important structure is the lobe in the salt range thrust in this part, and connecting them is a transfer zone, what we call as Kalabakh part zone. So these kind of structural observation on surfaces are really important to understand that there is some sort of factors that are controlling these kind of structural variations. So what we do is that then we look at the correlation. So in this case, you can get the correlation from the surface stratigraphy. You go, you find the sections, you measure them, you look on the facies, and then also for the subsurface, you can look down into the wells, and then you correlate them together to see how the sedimentary wedge is present in this area. So in this case, what I have found out are from the previous work of other people and from the well data, that the stratigraphic wedge is tapering towards south, and what you can see in the Kohat area that all the thrusts are containing Eocene stratigraphy on the surface compared to the Potwar, where you don't see that instead of the salt range. So what first guess you can get from this kind of analysis is that there are maybe two decollements present in Kohat and a single decollement present in the salt range below the stratigraphic wedge above the basement. Then looking at the structure style, people who have worked in Kohat, they can understand that this is not an easy place to understand the structure style or just on the surface stratigraphy. So if you have seismic, that gives you an additional constraint on the subsurface geometry. So what I did is I combined the surface structure geology with the seismic, and what you see here is that in the seismic, in the upper 1 to 2 seconds, into 2 seconds of the seismic section, you see kind of discontinuity in the structure patterns. And down below, you see kind of repetition, so which I interpret it in terms of the surface geology is coming out of the upper decolma, and below upper and lower decolma, we have kind of duplexes present that is repeating the stratigraphy and thickening the tectonic wedge. So this was the cross section which was developed combining both of them. So in the northern part, you can see is that the surface structures are only limited in the upper 1 to 2 kilometers. And when you go down in the section, you see the repetition of the strata. And up to this Banda Lahuni thrust and Vaso thrust, you see double decolma structure style, and down in the Sugar, again, we see a single decolma structure style where whole stratigraphic package is taken southward on top of the Karabakh re-entry. And then looking at the Potwar, most of you are well aware of the structure geology in this part. In the northern part, what is commonly interpreted on all the seismic lines, this is the pop-up structures, triangle zones in the northern part, and then in the southern part, the stratigraphy, the structure geology is quite simple. What you see is that salt is present at the base above the crystalline basement, and then we have the platform strata, and top of it is the new gene foreland strata that is uplifted along the salt range thrust towards south. And then looking at the structure cross section, you see these geometries taken together and putting it here. And what new is here is the fault bent fold in the form of salt range that is present in the southern part of the cross section. Yeah. What I found out is that when you put together all these cross sections and then understand the structural style transition from one part to the other, you can see that this double decolma structure style is slightly vanishing toward the Potwar side. So this more or less dependent on the evaporites available in the Kohat area that are providing a double decolma. For the Kohat, while you go toward the Potwar, it more or less goes toward the single decolma structure style. And what you see in the transfer zone, what I found out is that salt is playing a really important role. It is extruding out in the footwall of the Kalabakh fault. If you have done field work here, you will see that these salt diapirs are exposed in the Chinji formation. So these salts are actually diapering out into the younger strata, and also this salt is migrating towards south, forming this bend in the salt range thrust in this case in the transfer zone. So my understanding of the Kalabakh fault is that now it is more the main strand of Kalabakh fault is acting more as a normal fault instead of a thrust fault in this region. When you restore the cross section, you see that on both ends of this structure style, you see that this is about 40 kilometers of shortening is accommodated. So structure style is different, but the magnitude of shortening is the same, which somehow gives you a kind of really new interference into the structure style, that how different kind of magnitude of same magnitude of shortening is accommodating through different structure style. Then looking at the development of the salt range, so now you understood the structure geology, but what we are interested more is when these faults are formed, then we need some methods to understand, to constrain the timing of the faulting. For example, development of the salt range, what I used is apatite fission track and apatite helium data. How it works is that the rocks data containing zircons and apatite, when they cross certain temperatures like 120 degrees centigrade for apatite, 240 degrees centigrade for the zircon, they start to accumulate fission tracks in their system. And when they cross 80 degrees centigrade, they start to retain helium into their crystal system. And when they are exposed, or they are eroded from the source region, like what we have in northern Pakistan today, all these strata is deposited into the sedimentary basins. And if these these rocks in the form of these sediments, they go down into the sedimentary basin and they go above the temperatures, like 120 degrees centigrade or 80 degrees centigrade, all the fission track and helium diffuse out of the system. It goes out and all the history of the source region is vanished here. But if it has not crossed this temperature, for example, in this case, this sediment coming up, and for example, in this case, this 4, you can see, this 4 number rock, when it was deposited in the form of sediments here, it was not buried enough. So it still contained the information about its source. But this rock, like 1, it has almost uh, erased the source history. So we are important to see if you have the rock coming out of this area that is unreset. If you have rock coming out of this region, this is partially reset. And if you have rock coming out of this area, this is totally reset. For example, when these sedimentary basins are transformed into fold and thrust belts, these rocks are again uplifted towards the surface. So, for example, in this case, rock coming up from the Strait of 1, that was coming from the hot region, so it has now the new history, new fission tracks, new helium into the system. If they were coming from 2 and 3, they would have partially reset some source history. And if they had coming from this 4 toward the surface, then they have totally source history available with these rain rocks. So we can do these kind of things to understand the timing of thrusting in this region. So what I did is that I have collected samples from all this area in the salt range, from eastern, central, and western salt range. And most of you know this is Kevra section, this is Karoli, this is Pale, this is the western salt range, this is Wundi Lobe area, and this is the data that I produced in that sense. Can you hear me?
Yes, we can hear you. Please continue.
Okay. So this is appetite fission track ages in the form of squares. And what you see here, these circles are the appetite helium ages. And the color codes are from where I have taken them. In this case, the brown are the Cambrian. Cambrians are the Kevra and Cossack formation, and Permian are the Tobra, Dendot, and Warcha formation. So, and this one is the Kamlial formation. What you see is that the ages are quite dispersed, like from 4 million years here to 350 billion years. So this gives you a kind of very different large dispersion that need to be solved. So when you look at the stratigraphic wedge, you see in the northern part, in the southern part along this salt ranges, the stratigraphy is more or less 1.5 to 2 kilometer thick, and when you go toward north, you see it goes to about 4 to 5 kilometer thick. So this age, 350 million years from the Tobra granite, all of you know most probably, and then this age is what is really important is that when you see these rocks, this represents that when you go toward north, the samples are coming from the greater depth. So this sample was coming from the deepest part of the section. So this was reset, totally reset, 4 million years, and these edges are partially reset. So now coming toward doing the thermal modeling on top of it to contain the time temperature history. So what I did is that I thermomodeled these samples individually and then combining them together, and then all of the samples together in one thermal model. So what you see is the result that these Cambrian samples, when they came into the basin at around 550 to 500 million years in the Cambrian time, they were deposited, and then they were kind of heated to the temperatures of 80, 90 degrees, and then they were exhumed. And then afterwards, in the Permian, these blue lines you can see is the Permian strata coming into the basin, and they were again deposited and they were heated to a certain extent. And then finally, after the coming of molasse into the system, what we had is that these strata were again deposited on top of this platform strata, and they were heated to 80, 90 degrees. So what we found out is there is one exhumation or cooling event in the late Paleozoic, and then there was another event in the early Pliocene. So what was the early Paleozoic event? That was related to the late Paleozoic rifting that is widely reported in the Peshawar, in the Kashmir, and in the Zanskar area. What I, what I assume is that after the deposition of Cambrian strata, on top of Cambrian, we had deposition of Ordovician Devonian strata on top of it, like what we see today in the Kohat, in the Potwar, in the Peshawar, and also in the Abbottabad ranges. So this strata was kind of eroded during the late Paleozoic time when normal faulting was happening in the Salt Range and in the other parts of the Himalaya. And afterwards, in the Permian, the new strata came out into the basin and filled on top of it. So forming one of the major unconformity in the salt ranges. Then coming to the early Pliocene event, that is the development of the salt range. At 4 million years, our samples were near to the ramp in the in the north of salt range thrust. And from 4 to 3 million years, that all the strata was uplifted along the salt range, and there was maximum cooling on the ramp when the molasse or Neogene foreland strata was eroded from top of these platform sequences. And from 3 to present day, what we had is that this Potwar salt range thrust sheet is gliding towards south, forming the Falkland fold in the salt range. And the third part of my talk is related to the structure chronology of the Kohat. What I did is that I collected samples from the Kohat, from the hanging wall of the major truss. So what you can do is that you can only collect the samples from the sandstone because limestones don't have zircons and apatite, so you cannot use them for these kinds. So the clastic sedimentary strata is really important to have to do apatite helium or apatite fission trig dating on top of them. So what I found is that the ages were spread out in this spot. I had older around 9, 10 million years ages on the MBT, and then I had younger 10 to 3 million years ages in the Kohat. And what was really surprising was the older age of 13 million years, apatite fission track date in the Surghar range. And these were the older ages from 1995 Meeks data, which were around 9, 10 million years, which were the first one to constrain the development of main boundary thrust in this area. So what I've made is a structural cross section to look in the structure style of this area. So what you see is that south of MBT, whole structure style is decoupled above the Paleocene Eocene. And what below is duplicated in form of one thrust sheet riding on top of another towards south. And all the structure style present at the surface is decoupled and has nothing to share with the structure style below it. And when you go towards south, you can see a very simple structural model here, one main range front thrust coming out and bring all the strata on top of it. So then I restored these cross sections and I got the estimation of about 100 kilometers of shortening in the Kohat area, including the MBT. So these kind of structures, when you see they are, when you make them, then you have to understand the structural evolution style or structural evolution model for these kind of structures, how we can simulate or how this deformation has propagated. So in this case, what you can see here is I had developed a forward model that is based on the deformed structural cross section from my deformed cross section and the restored cross section. So what I did is that I connected the lower decolma with upper decolma to simulate the deformation and see if I can produce the similar kind of structure what I see in the deformed cross section or what I modeled actually. So my idea of structure propagation here is active roof thrust model. This starts with a kind of really early 15 to 12 million years development at the salt range, at the Surugar range. That was like then followed at the same time with the regional erosion of Rawalpindi group in the southern part. And then from 12 to 8 million years was the time when the MBT was active in north of the salt range in the Kohat Potwar. And from MBT, what we see is that the deformation is propagated on the upper decolma. And what you see down is that the lower decolma is creating the wedges or duplexes that is uplifting the upper strata on top of it, and also it is carrying them forward and rotating the older thrust. And this is the time like when you push all this cross section towards south, and what we see in the subsurface is the tectonic thickening, and above the roof thrust or above the upper decolma is kind of massive erosion of the strata, which is actually giving us the cooling edges of the wedge. And this is what we see today, that there are some local asperities that are active that generate earthquakes in the Kohat area as well. And also the salt range, Surga thrust is active today. So this is how the deformation has propagated from south toward north. And then we compare them to see how successful we are in developing or simulating these kind of structures in this sense. So here you can see that we have produced quite nicely the same kind of deformation pattern, although it is not really equal to what we see in the deformation style in the deformed cross section. So now shortening, coming on the magnitude of shortening, what we had is like 75 kilometer in Kohat and 65 kilometer in Potwar. And then sequence of deformation, in my opinion, or what my data shows, is that it started earlier at the Surgar, then it was followed by main boundary thrust. And then from 8 to 2 million year deformation propagated in the Kohat. And from 4 to present day, softening thrust is active. And from 2 million years to today, what we see is that this part of Kalabakh part zone is active, that is exerting the first kind of control on the southeastern part of the Kohat, where you can see is that these current thrust, Hukni thrust, they are changing their strikes, and the salt is actually migrating towards south under the Gundi lobe. So here I think Moban Faisal, Naveed Hassan, and all the other people who were organizing this event, thank you so much and for being patient and listening to my talk. Thank you so much.